Then another lossless data compression technique that was given by Shannon Fano. So here again we are see, in this particular technique also the see different techniques have been devised with the with the single objective of reducing the amount of memory required for the storage and the amount of time that will be required to for data communication. So in this particular technique, what do we do? It is also based on the frequency only. It is also based on the same technique. You can say that the frequency. There are certain characters which are high frequency, and there are certain characters which are low frequency. But they have considered the same information, but the methodology to create the code is different from what we did in the Huffman coding. So in this particular technique, we sort the list of symbols in the decreasing order of the probability. So you can see the probability or the probability or the frequency is same thing. So either you can have the probability of a particular alphabet in the given text, or you can have the frequency of the particular alphabet in the given text. So you can say, so in this particular technique, what is being done is we split the list into two parts. So with the total probability of both the parts being close as much as possible. So here you can see, first of all, we are going to sort this particular thing, and we are going to find out either the sum of the frequencies, or you can see the sum of the probabilities. So if we are able to find, let us say, if we take the sum total of A and B, and we take the sum total of C, D, E, and E. So what is the, if they are coming very close to each other, that means the difference is less. We are going to partition this particular table at that particular level. So you can say we can divide A, B, and C, D, E in between if the difference, let us say, it is sum of A and B is 50, and the sum of 30.35 and 0.45. So we can divide it between A, B, and C, D, E into two parts. So after every division, what do we do? After every split, we assign the 0 to the left part, and we assign 1 to the right part. So, and we keep on repeating it until all the symbols are split into individual groups. So you can see, we are in the Huffman coding, we were following the bottom-up approach. We were considering them as the leaf node first, and we are moving from bottom to top, creating the root node. And here you can see we are applying the top-down approach, and we are moving from top to bottom and creating the individual leaves at the end. So these codes are considered accurate only if the code of each symbol is unique. So here you can see the same example. So what is being done? So the total is being taken. The data is sorted in the decreasing order of their probabilities, and on the basis of that, the split is being done. In this split here, you can see the appropriate split has been found at you can B. So the DB and is taken on the one as one child, and AC is taken as another child. So here you can see, so the left child is assigned the 0 value, and the right child is being assigned as the 1. So in that case, then similarly, now we see in the left child, we know we have only two nodes. So you can say, all the two characters, we have to just split them. So the left will be assigned 0, and the right will be assigned the 1. So here in the right hand side, we have three characters. So we can take a sum total of, we can see that A is 0.22, and we combine, if we take A and C, if we can't try to split at C between C and A, so there will be unbalance between the two. So we are going to split A and C. So because the sum total of C and A is more or less closer to A. So what do? We are splitting that at the C. So we get A as a leaf node, and then we have and we are assigning 0 on the left hand side, and we are assigning 1 on the right hand side. And then we say we are left with C and E, and we just have to split these two characters. So when we are splitting now, since at every level we have zeros and ones, and now converting getting the code for this particular getting the codes for each character from this root, we know we have to read through the leaf node. So here you can see the code for D is 0 0, and the code for you can say B is 0, 1. So here you can say here we have the both in the Huffman coding as well as in the Shannon Fano coding. In both the techniques, we are getting the variable length codes. It may mean that some characters are having a codes of a single digit, and some characters are having the codes of the 2 digit, 3 digit, 4 digit, like that. And this helps in this kind of you can see these variable length coding techniques. They help us in reducing the memory, because the small number of digits means the small number of bits which are required for the storage. So therefore, if we have to find out the code, you can start from the bottom also. So here you can say one. What is the code for C? 1, then 1, and then 0. And the code for E is 1, 1, and 1. So we are moving from left to right and right to left. And so traversing each part of the tree, you can say for every branch, because it is leading to one character. So every branch of the tree is representing the code for the leaf node, or because leaf node is having a particular character from the text. So this is how we use a Shannon Fano coding for creating the codes, or you can say for the data compression. Now, since we have been using this, so the question is how much memory we are able to save when we are using these techniques. So here you can see if we have these symbols A, B, C, D, E, and we are using the Shannon Fano coding, let us say we are able to generate these codes. And then if you see in the occurrence in the 100 character length text, it takes this much of space. So here you can see the number of bits using the ASCII code for this when we are using the 22. So here you can say if we see the occurrence in number of bits which we require for storing the character symbol A, it requires 176 bits. But when we use the Shannon Fano coding, it requires 44 bits. Similarly, for B, C, D, E, we can calculate the number of bits which are required using the ASCII characters, which are used on the fixed length encoding scheme by the machines. And here you can see the number of bits which are required while using the Shannon Fano code. So here you can see the total length when we take the sum total of A plus B plus C plus D plus E, because that is the total memory requirement for all the characters. Using that ASCII codes, it requires 800 bits, and if we see the Shannon Fano coding, it requires 220 bits only. So it is nearest multiple of 8, right? So the text needs only the 30 bytes, whereas using the ASCII code, text needs 100 bytes. So you can see the difference. We are able to see able to save the 70% of the memory, or you can almost using the Shannon Fano coding. So this is the similar kind of you can say calculations you can check. So you just, because the ASCII character requirement will be same, but for the Shannon Fano, you can say that using the Huffman coding, you can see the encodings that we have used. On the basis of that, again, you can calculate the number of bits which are required, and you'll be able to see. So whenever we are using the text compression techniques of Huffman coding or Shannon Fano coding, we are able to save almost 40 to 50%, 50% of the memory for the text compression. So now you have to do this question and tell me the solutions for this. So this is the you can say these are the frequencies which are given to you for some text. Now you have to encode the given text using the Huffman coding as well as Shannon Fano coding, and then you have to calculate the number of bits which are required for storage using the Huffman as well as Shannon Fano coding. Start working on